Here's our second lecture on second-order linear, non-homogeneous, possibly, differential equations with not necessarily constant coefficients. And this is the new part, not necessarily constant coefficients. And you can always write these differential equations in this form. This is basically what we mean by these adjectives here. The non-homogeneous part is this not being 0. The not necessarily constant coefficients is these a, b, and c possibly depend on time. And there was a typo that someone caught in the previous video where I forgot to write x here. All right, so from this you can divide by a of t. So I'm going to simplify this down a little bit to make our calculations easier. You can just divide everything by a of t. A of t is definitely not the 0 function. If it were, then we would not be looking at a second-order differential equation, right? So you can divide everything by a of t. Then you have like b of t over a of t, just call that p of t. C of t over a of t, just call that q of t. And capital F of t over a of t, let's just call that lowercase f of t. So we can get it to look simpler with just a 1 coefficient here. And important reminder, this is still a linear differential equation. No matter how complicated these functions of time are, even if they look like, non-linear things are being done to the variable t, like sine of t and t squared and t cubed, all kinds of crazy stuff can happen to t. It'll still be a linear differential equation if this is the form it has. Again, what I mean by linear is that it's a linear operator being applied to x, showing up on the left-hand side, with just some vector function in this case showing up on the right-hand side. So in this case, the linear operator being applied to x on the left-hand side is take 2 derivatives, so that's what's being done to x there, take 1 derivative and then multiply by the function p, that's what's being done there, and just multiply by the function q, that's what's being done there. So in the previous lecture we saw just one specific version of these where for a, b, and c of t here you have like t squared, t, and 1, possibly scaled by different coefficients. That was Cauchy-Euler differential equations. That was a really, really specific case, right? So what do we do in general when you have other kinds of functions of t sitting out here? So we can partially answer the question, but not fully. Sometimes it really is just too hard. Well, first of all, let's remind ourselves about the things that do work no matter what, the things that work just because you have a linear differential equation. So because it is a linear second-order differential equation, you can apply the same idea that you would apply to any one of these Lx equals f kind of differential equations. Step 1, so if you want the general solution to this, step 1, get the general solution to the homogeneous differential equation. Step 2, somehow get some solution to the non-homogeneous. And step 3, add them, and then you'll get the general solution to the non-homogeneous. So this always works just for all linear differential equations. The problem is that steps 1 and 2 might be hard, right? So when the coefficients are constant, for step 1, you guess e to the lambda t, right? When you have constant coefficients, you just guess e to the lambda t, and you get some polynomial for lambda. And eventually that leads to 2 linearly independent solutions for the homogeneous differential equation. So that's when the coefficients are constant. And then if the coefficients are constant, then we also have some approach for number 2 that kind of works sometimes. And that's the method of undetermined coefficients. So here in the constant coefficients case, these are the tools that are available to us. And that's why we can pretty much handle that case, except for, if the function f on the right-hand side is very complicated, or isn't very special, isn't one of the ones that we know how to handle, then we'd probably be stuck. So that is a limitation, but at least this part we can do. Okay, so that's for constant coefficients. For Cauchy-Euler, which is another special case, we guess t to the m, right? And then we can also kind of use the method of undetermined coefficients if we're clever about it. There's just one homework problem where you're given a suggestion for how to do that. But yeah, we can at least do step 1 for this. What about in more generality? So the method that I'm going to show you in this lecture is called variation of parameters. And the way it works is it assumes you already did this. So it assumes you somehow completed step 1, which is hard, but you might have been able to do it in some particular case. And then it gives you a method that always works for completing step 2. So variation of parameters, the method I'm going to teach you, tells you how to do step 2 using somehow what you did in step 1. And that's pretty awesome, because as you know, step 2 is kind of hard, right? The method of undetermined coefficients is pretty limited in what kind of functions on the right-hand side it can handle. Maybe I should write here, if already done. So if you have already done step 1, then variation of parameters can help you with step 2. Okay, so assume that we have somehow managed to do step 1. So assume that we have a general solution for this homogeneous differential equation. That means we found 2 linearly independent solutions, right? Like what your textbook calls fundamental solutions. So we've got 2 linearly independent solutions, x1 and x2, to this. So that means L of x1 is 0, L of x2 is 0, and they're linearly independent. So your general solution is like c1 x1 plus c2 x2. Then what we're about to show is a way to do step 2, this somehow get some solution to the non-homogeneous, by using step 1. And it's called variation of parameters. Okay, and I want to just describe ways in which it's useful and ways in which it's not so useful. So the useful thing about it is that it's a general method that always works. When it applies, it always works. So it always works to get you from step 1 to step 2. Which is a little bit weird of a thing to talk about, going from step 1 to step 2. That's a little bit weird to us because with all of our previous approaches, step 1 and step 2 have kind of been totally independent, right? You don't use step 1 to do step 2, right? Like step 1, for constant coefficients, you guess e to the lambda t for step 1 and then you get some stuff. Then you might use the method of undetermined coefficients for step 2 and you get some stuff. But you don't use the information from one step to do the other step. Just at the end, you would add the results. But for this method, it will use the information from step 1. Assuming you finish step 1, it will always work to get you to step 2. Okay, so that's the good thing about it. Some bad things. Well, what I'm saying as a good thing here is kind of a bad thing also. It needs step 1 to be done, to be already done, which can be hard. Okay, if you have constant coefficients, it's not hard. You just guess e to the lambda t, and then you've got the 3 cases. If it's a Cauchy-Euler equation, that's not hard. You guess t to the m, and then you've got your 3 cases. But what if it isn't either of those two? Like most choices of what you would pick for p of t and q of t here, or a, b, and c here, most choices are not going to be constant coefficients or Cauchy-Euler, right? So those are just 2 very special examples. All right, so this needs step 1 to be done, which we can only do sometimes. It's often hard to do step 1. And the other disadvantage I would say is if you're expecting a nice, beautiful solution at the end, usually it doesn't give you that. Usually leaves you with gross integrals, which I guess it's a matter of taste. Maybe you love integrals, but usually it'll give you an integral that you just have to keep in the form of an integral. So your final answer will just be the integral of this function, whatever it is. I don't know of any simpler way to write it. So that's usually where you end up, which is sometimes unsatisfying, but also sometimes perfectly fine, and definitely good, right? It's at least getting you to a solution, even though you haven't written it in the simplest form that you could write it. Okay, that's it for the intro. So in the next video, we'll show you how to do variation of parameters, how this works, which gets you from step 1 to step 2, assuming you did step 1.